So in this video, I'm going to talk about the capacity design versus direct design from the structural response point of view. Okay, it's not detailed capacity design and direct design, but actually it is a kind of perception of the capacity and the direct design from the response of the structure. I'm going to talk about like strength versus ductility-based response. I'm going to talk about hints only about direct design, what is the meaning of it, and the capacity design. And the last item is going to be dedicated for the member versus system level consideration.
Now let's talk about something else which is related to the strengths and the ductility or versus ductility-based response. Okay, so that's our main topic for the next two slides here. A couple of slides here we're talking about strengths and ductility-based response. It's another concept, you need to understand it well. Okay. In order to give an introduction to this, we need to understand that there are different approaches to seismic demand in general. Because understanding this hierarchy or these kind of different approaches going to give you very good understanding of the strengths versus ductility-based response. Why we use, take care of this word strength and the word ductility. Okay, now we understand at least what is the meaning of the strength, what is the meaning of ductility. And based on these kind of responses that we have explained before, we are going to understand what is the main approaches, the main different approaches for seismic design. Okay, and remember well that people and professionals and academic people and professors, they are always concerned with the structure response, and based on the response we can put the appropriate seismic design technique or approach. So based on this, we are going to find that our seismic design can be categorized into two main categories. The first one, or the first design approach, we call it direct design approach. And the second is capacity design approach. What is the meaning and what is the difference? I'm going to explain. Direct design means that we are going to find what is the required forces on the system, and then we're going to provide the enough design level or enough design, or we can say the force that is going to be used for design is going to be coming from the analysis directly. This is why the word direct has been used here. From the analysis or from the structure analysis under the lateral load, we're going to find that this column or that beam needs a certain level of force to be designed for, which is like 100 kilonewton meter, for example, as a moment for a beam. Then we're going to design the element based on this level of force. So this is why we call it force-based design. It means that the force that is going to be induced during the structure analysis, during the direct structure analysis, we're going to use it for the design of the different member. And whenever we use the force, then we are going to be sure that the component is having enough force capacity. So our main parameter here is force. However, there is another approach under the direct design, but instead of using force, we're going to use deformation. Okay? Sometimes we are not concerned with the force, but we are concerned with the deformation, especially inelastic deformation. So in this case, we are going to talk about ductility-based. As we said, ductility, you understand now what is the meaning of ductility. The ratio between the ultimate deformation to the yield deformation. So sometimes here we are concerned with this. We are going to design our system based on the capacity or the deformation capacity, especially the inelastic. So we are going to, based on our structure analysis, instead of checking what is the forces that is going to be induced, we're going to check the deformation that is going to be induced. And based on these deformation, we are going to design our structure based on ductility-based design. We call it ductility-based. And the main parameter here is going to be the deformation. So if, for example, the drift of a story like 1.5%, then we're going to check this is the maximum drift of the building for this specific floor. Then we're going to say that we want to design this building to resist or to accommodate 1.5% deformation. Okay, so this is based what we call it, this is ductility-based design, where the deformation is going to be the main input parameter. On the other hand, we have a different approach for the design. We call it capacity design. Capacity design. In the capacity design, we are going to use some elements. We're going to assign them to be inelastic, and we are going to allow high deformation capacity for some elements. However, other elements in the structure, we are going to allow them to be in their elastic range, and they are going to be designed based on high force capacity. We are going to look or design them based on force. But here we're going to design these elements based on deformation capacity. I'm going to talk about this in detail, okay, shortly. So don't worry about this, and I'm going to explain what is the difference between direct design and capacity design in an example right away. Okay, so this is the main philosophy behind the different seismic approaches. Okay. Now let's go into the details for the direct design. So direct design is dimensioning of individual components to resist locally evaluated actions with no due consideration to action redistribution effects in the system as a whole. So remember this very well. In the direct design, here in general, as I said, we just try to get the structure analysis from the seismic excitation, and based on the structure analysis forces, for example, we design the elements, the beams, columns, connections, foundation, and so on. But we do not say that what will happen if one beam is going to drop the load or goes to the inelastic range. What will happen here? We do not think about this. We do not take it into consideration. So that's the point here. The direct design is dimensioning of individual components to resist locally evaluated actions. This is the meaning of structure analysis, with no due consideration to the action redistribution effects and the system as a whole. This is very important. On the other hand, if you go back to the capacity design, as I said, we are considering some elements to what? To deform in the inelastic range, because we are defining or we are designing some elements to resist based on high deformation capacity. So we are considering here redistribution of loads, and these elements are going to be designed for or after redistribution of force. So this is why capacity design is considered to be superior compared to the direct design. Okay, in direct design can be either ductility-based or strength-based. Already we have mentioned about this, force-based or ductility-based, and we mentioned about the difference between them. The main difference is here, force is going to be the main parameter for the design. Here, deformation, inelastic capacity is going to be the main parameter for design. Okay. Now, for the force versus ductility-based seismic design, we want to understand it clearly or more, which is this part here if we're talking about force versus ductility. Okay. Force versus ductility-based seismic design. Traditional force-based seismic design has relied on force capacity to resist earthquake effects, expressed as a set of horizontal actions defined as proportional of the weight of the structure, right? And this is common actually. Whenever that we are under the design of the design stage of our structure, as I said, we put some inverted triangle. You know why it is not working here, sorry. So we are like putting some, as I said, some inverted load, and we say this is how the earthquake is going to affect our building. And then based on the analysis, we are going to bring the moment here and here and here, and or the shear and the bending and shear for the columns, and then we are going to design based on the force capacity. Okay, so if the force or if the analysis gives us like certain amount, 100 something, then we're going to design the beam to be 110 or 120, and we say that we are having a factor of safety of 1.2. That's it. And how much this lateral load is, it is a fraction of the weight of the structure, coming like 5%, 10% or something like this. However, this is the classical way for our design. We have another type, or there is for the last, especially in the last or in the past 20 to 30 years, there has been a tendency to substitute ductility for strength. Okay, so we started to realize that, well, if this is the case, actually our beams and columns, they can go into the inelastic range, and we can utilize the inelastic stage or inelastic part of our elements and structures. So not only at the yield, but still we have some part here we can utilize. So why not? So this needs to be, as we said, described by ductility. Okay, this needs to be described by ductility. So at the last almost 30 years, there has been a tendency to use ductility, okay, for strength instead of strength, because ductility is going to be like more economic in one point. Okay, the cross sections is going to be lighter, but it needs more man workshop. Okay, so if we want to like summarize why we have used strength-based in comparison with ductility-based, so actually here the word uncertainty comes. Let's read this. It is developed, strength-based, developed in recognition of the great uncertainty associated with estimating seismic demands. And this is true. If we have our structure pushover curve here, and this is the yield point here. Actually, whenever that we are designing our structure, we say that our structure is going to be here. Let me put it in like bigger space. I cannot have, okay, let's have this. This is here better. So if we're talking about something like this, if we say this is the yield point, then our design level is here. This is the design level here. But the yield level, this is V yield. Let's call this is V design. Actually, because we do not know how much force coming from the earthquake. So there is an uncertainty is involved here with estimating the seismic demand. So we are using some factors that is highly overestimating the seismic demand. So this the inverted triangle, highly estimating the seismic demand. It's not like this. The seismic demand supposedly to be far less than what we are using. Based on this, we use the strength-based to counteract the uncertainty involved. Okay, as if someone that he doesn't know exactly how much he should pay for a certain service, for example, then he pays like a huge amount of tip or huge amount of money. This is the same. This is the same strategy. But after 20 or 30 years, we realize that no, it's not like this. We need to be more economic in the way looking to our design. So ductility-based is significantly less sensitive to unexpected increase in the force demand imposed on it than its strength-based, because we are not thinking about how much the force is going to come here, okay? Actually, we are talking about how much deformation is going to be induced. So we are talking about ductility here, deformation, not force. Okay, So we do not care how much the seismic demand exactly would be. So this is why the word less sensitive has been used here. But we are caring about the structure, how much it can provide. What is the maximum for the structure itself? Structure for ductility-based, they are lighter and use less material, but more workmanship. Okay, so they are lighter. Lighter because, why they are lighter? Because whenever that we give more detailing for the components, then they are going to have less forces. The forces that is going to be absorbed, the seismic demand is going to be less. So this is why the cross section is going to be less, because the seismic demand is smaller. Instead of receiving 100 kilonewton meter, we're going to receive only 80 or 70 kilonewton meter, because the structure characteristic itself does not allow higher demand to be taken. Okay, and less material, this means what? Economy here. We are talking about something economic, lighter, economic. Okay, so this is really attractive for stockholders and for the decision taking and the building owners and so on, because it is going to cost them less. But actually the point is it has skilled workmanship and more workmanship, because we are going to put more details in our components and elements. Okay. On the other hand, the capacity design is totally different than this. The capacity design now, it is the modern understanding for whatever that, or for the seismic design. Okay. Capacity design, I'm going to explain it here based on this figure. In capacity design, think about it as a chain. Think about the whole structure as group, or this chain. Different circles here are connected together. The point is, we are going to choose one circle and we are going to make it from ductile material. We call it the ductile link, like rubber, for example. Think about this as rubber and think about this to be wood. Okay? Okay? So this is why we put here, this is ductile link. We put this as brittle links and brittle links. And we applied our forces, which is considered to be the earthquake that is going to be applied here. But now think about the structure to be the chain of these circles, and the force being applied, which is pulling force or under tension, it is the earthquake forces. What will happen here? If you apply more forces, if you apply F2, which is larger than F1 from both sides, you are increasing the demand, you are increasing the pulling force here and here. What will happen for this ductile link? Exactly, it will elongate. Large inelastic deformation will take place. However, these links, they are going to stay as they are. They are elastic. They are not going to break or fracture, right? So we allow more forces to be applied, and we will let this link to work with its own capacity, but we are going to allow this ductile link to deform in a large inelastic deformation fashion, in a large inelastic deformation fashion. Okay, so this is actually what will happen for our structure. Okay, now let's read the narrative here and you're going to understand what I was saying. Capacity design employs a mixture of members with high load capacity and members with high inelastic deformation capacity. So brittle links, they are high load capacity members here and here. This ductile link, it is what? High inelastic deformation capacity. To optimize the response of a structural system, this is achieved by identifying a failure mechanism. This is the meaning here. Failure mechanism means that if we have a structure like this, okay, and we have different floors and beam, okay, columns. So we can assume that I want, for example, the beams at the first story to deform inelastically, and the column at the first story to deform inelastically. For example, this is what I am designing for. I want the mechanism to take place here. So I'm going to design this column and this, the three columns here, to be ductile, and these beams, for example, to be ductile. So they are going to be the ductile link for me. However, the other columns of the remaining floors are going to be, they are going to be the brittle links. We will not provide them with detailing, just we are going to put them based on the capacity. What is the forces applied and what is the capacity that they should consider. Okay? Okay. This is achieved by identifying failure mechanism, as I said, the members and regions responsible for its development, and providing these members and regions with adequate ductility. In parallel, the rest of the structure is protected by providing it with adequate strength to ensure nearly elastic behavior. So we have like this one, which is elastic behavior in all other members, Okay. Okay, let's go to the next. Let's have a comparison between direct and capacity design. Like an example here, it's only for illustration. It's not a real numerical example, but it's only for the explanation purposes. So first of all, let's look to what we have here. We have a lateral load that is being applied on a frame, as you can see. We have gravity loads here, and we call this the applied actions, gravity loads, and the lateral loads coming from the seismic design based on equivalent static force method, for example. Under these loads, we are going to make our structure analysis, and we are going to find that we need, at this particular beam at the first floor, we need a required moment with the quantity of, or the magnitude of MP, for example, MB. Okay. Now these are considered to be the design actions. In case of the direct design, we are going to simply say, if this is MB, then we need the moment that is going to be in the first column is going to be MC11, and M in the second column, which is MC1, that in the second floor column, which is MC means first column, and 2 means that the second floor. So we need these three different moments to fulfill the equilibrium equation of the joint, which means MC12 plus MC11 plus MB equal to 0. This means that the equilibrium equation of this joint is going to be maintained here. Remember, MB is coming from the analysis and the actions coming from the structure analysis directly. This is the direct design, and this is commonly what we are doing in our classical way of designing. However, for the capacity design, it is different. We are not going to take MB as it is. Rather, we are going to put a beam, and this beam, we are going to consider the overstrength of the beam here. The cross-section that is going to be used here, we are going to consider, for example, if this MB, for example, and it requires a cross-section of a beam, if we're talking about concrete beam, like 30 by 70 centimeters, okay, cross-section, then we're going to put it here, but we are going to say that the moment that is going to be resisted by this beam is not MB, it is going to be M prime B maximum, which is the maximum. This is, let me use the red color. So this is M, so this is M prime for the beam, which is maximum. What is the meaning of maximum? It equals, for example, 1.2 times MB. What is 1.2 this? This is the overstrength factor. What is the meaning of overstrength factor? Remember that what we have explained before. It is a parameter or a factor that takes into consideration the difference between the required and the actual. This is the required moment. However, the actual moment that is going to be provided by this beam is going to be M prime x. So if we say that, for example, this is going to be 100, then M prime or MB maximum is going to be 120. Okay? Then the equilibrium equation at this point is going to be MB maximum plus, yes, M prime C11 and M prime C12. What is the meaning of this? What is MC, M prime and M prime C11 and M prime C12? Actually, this M prime C12 is going to equal to the same factor, which is 1.2 times the original MC12 that is already was here. Okay, and MC11 equals to 1.2 times MC11. Okay, this is only a ratio that I have put. It is 1.2, but actually this 1.2, it is what? Exactly, it is MB maximum over MB. This is the overstrength factor that we are going to talk about. Okay, so based on this, you're going to find that the actual actions that is going to be used for the design of columns in the capacity design approach is going to be higher than the amount or the magnitude of the moment required for the design in the case of the direct design for the columns. And the beam is going to be designed under the capacity design approach using the overstrength factor, which is higher than the required bending moment from the structure analysis. How much? What is the ratio between MB and MB maximum? It is going to be the overstrength factor. MB maximum equals to 1.2 times MB. Okay, so this is actually gives us what is the meaning of this, what I have said here. So this is MC12 and MC11 and MB. They are here. They are moments on the two columns and the beam respectively evaluated from the applied actions. These are from the applied actions. However, M prime max, B maximum, which is this one, is the maximum capacity of the beam, the member responsible for energy absorption in the weak beam strong column design approach. So under this approach, which is already we are designing, this is the philosophy of our design, we're going to allow the beam to to deform with plastic hinges at the ends. Okay, taking into account various sources of overstrength, like what is the meaning of overstrength coming from where? Unintentional increase in material properties, rounding off of member or reinforcement dimensions, post-yield hardening, etc. So we are having different sources for overstrength. Okay, 1.2, it's only a factor or only a number that I've used, but anyway, it might be larger than this number, or maybe less. Okay, so that's the meaning here. Design actions, which is M prime C12 and M prime C11, are the product of MC12 and MC11 and the ratio between M prime B max over MB. They are therefore applied actions. Okay, so this example really gives to us how the capacity design is going to work in comparison with the direct design. Okay? Okay. Now let's go to the member versus system level consideration. I'm not going to explain it in details, but what I want you to understand here is that there is a hierarchical relationship between the local and global structural response. So we have like some items in our structure considered to be local and other items considered to be global. The material sections, and so if we're talking about material, for example, the material here, it has certain, for example, stress-strain relationship. And after that, we are going to the level of the sections. We found that the section, it has properties, and also this section, if we are using different section from the same material, we're going to find that it has maybe different force deformation relationship than this one, right? So we should consider this. And after that, if we consider this, we are going to have our member. This means that if we are going to talk about our member, if our member is a beam or if our member is a column, they are different, plus the connections. We are going to consider also the connection. This beam or column, it has its own force deformation relationship, and this joint also, it has its own force deformation relationships. And then the whole system, it has its own force deformation relationship. Okay? So we are having like different relations. We need to consider all of them. Okay? This is the hierarchy of the relation between the local elements and the global main system that we have. Okay? Material, sections, and for the sections we have members and connections, and every one it has its own force deformation relationship. We need to consider them in our seismic design. Every component, starting from material, going through the section, going through the element, whether it's a beam or a column, and then going to the connection, and then the whole system. Okay, so we need to consider all of these in our design. Okay.